large area two-dimensional heterostructures for photodetectors, a collaboration between INL and University of Minho. This project aims at building a large area photodetector with a two-dimensional materials heterostructure and achieve a better theoretical understanding of its working principles.
Two-dimensional materials are very interesting materials, are very important nowadays. You can have devices using these materials so thin that they are only a few atoms thick, and they can be useful in many applications, namely in flexible electronics, for instance, and things like that. We will show you how we are building these photodetectors, how we build these materials, how we can do these things.
For industrial production, these detectors have to have a large area. Chemical vapor deposition is the technique of choice.
The device is represented here on the screen. It's composed of different types of 2D materials. In this case, there are three different types of 2D materials. You have hexagonal boron nitride on the bottom. Then you have graphene here, represented by the blue spheres. In between, the transition metal dechalcogenide is this fairly complicated structure. And on top of it, you have another graphene sheet, and then you have metallic nanoparticles. The device works in a very simple way. You shine light, the metallic nanoparticles concentrate light on the transition metal dechalcogenide, and when this light is concentrated there, it produces two charges. One charge goes into the top of the graphene sheet, and the other charge goes to the bottom of the graphene sheet. So the graphene acts here as contacts to extract the charges from the transition metal dechalcogenide. So you know that light has arrived to the device when you see charges moving on the two graphene sheets. And this is something that you can detect because it's like an electric current.
The role of theory in this project is the following. The project is about photodetectors made with two-dimensional materials. And in a photodetector, two things happen, okay? The first is that light is absorbed by the material. And the second is that when this light is absorbed, electrons move inside the material and give rise to current and voltage, and that's what makes the detection happen. At the theory level, what we are doing is modeling these two processes. We're modeling the light absorption, non-trivial problem for theory because there are electron-electron interactions that determine this optical absorption. And we also model how the electrons move inside these structures made with these 2D materials.
This project has both a theoretical part, for better understanding of how the photodetector works, and an experimental part, leading to the production of a prototype of large area photodetector.
In the end, our goal is to fabricate all 2D materials photodetector, and for that we need graphene in the first place for the contacts to the active layer, which is a transition metal dichalcogenide. The graphene we can grow by chemical vapor deposition over large areas with a very high crystalline size, up to several millimeters in diameter. And this graphene has the perfect properties to work as an ohmic contact to the active layer made by a two-dimensional semiconductor. Graphene is grown in a chemical vapor deposition system, not very different from this one, where we use a copper foil as a catalyst for growth. And then it is transferred using a temporary polymeric substrate onto the final wafer, where we fabricate then the devices.
Understand how the device works theoretically will help us to improve the quality of device. Find even more applications like bio and molecular sensing.
So here I do 2D fumes. We usually do indium selenide or gallium selenide. And this is a machine that's called molecular beam epitaxy. The principle is that we throw beams of elements in the surface of a substrate, and these elements we organize in the 2D materials that we want. So these materials, they have the proper band gap of the wavelength that we want. So this material will absorb the light and convert in an electric current or electric voltage. Molecular beam epitaxy needs to happen in vacuum because the beam of elements need to travel some distance to reach the surface of the sample. And in this technique, we can control what element it will reach the surface of the sample by mechanical shutters that we can control mechanically.
The project involves several students that will receive an excellent training for their professional life.
Here we do Cvd Technique, where we use molybdenum samples to deposit selenium and form the final crystal, molybdenum diselenide. Inside this graphite box, we put the samples. Then, by the use of inert flow, we deposit the selenium and form the final crystal. Here, we insert the temperature that we need, we close the furnace, we wait, then we open to cool it down, and it's ready.
This is the system for chemical vapor deposition of our graphene samples. It is a hot wall furnace, which is in this compartment. Here you can see the load lock, where we load the sample in order to avoid contamination of the main reactor. And here you have a graphical user interface where we can control and choose all the parameters of the deposition, and we can also monitor everything that is going inside the reactor. This is the track where we spin the photoresist on top of the wafers, and where after exposure we develop the photoresist, and we process here the wafers where we fabricate the photodetectors. So this is a direct light laser tool where we transfer the drawings from the masks onto the photoresist before developing. Each layer of the photodetector has a particular layout, and the drawings are transferred to the photoresist by using this tool, which has a laser that works like a pencil and writes according to the drawing in the AutoCAD file, transfers this drawing to the photoresist layer, which is covering the wafer from the previous step in the machine we have just seen before this one.
Well, this is our Raman system. Confocal Raman system has 3 different lasers, and we choose the laser according with the properties of the material. This is a very important technique because it doesn't need the sample preparation, and we can have the fingerprint of each material. Then for production of a photodetector, we need to produce the active material and to do the characterization. We can also take out information if the sample is under stress or if it has some defects in the sample. This is very important because it will be the active material in the photodiode. Also with Raman, we can infer about the sample quality, if it is good to go to the next steps or if we can do a different improvement in the growth. The sample can be characterized sample point by point or making an area as is shown here in the screen. This is mainly what we do here.
Here in this lab, we do the electric characterization of our devices. So this is one example of 2D detector that we did in a whole wafer. So it's several detectors in this wafer. Here we can shine light in different colors. So as an example, here we can shine this green light, and then we measure some current there. And then when there is no light, this current drops a lot. So it's an example that how sensitive it's our detector to the light. this we can look at the wavelength that we want to and also try to improve our detector.
This project opened new interesting possibilities on the research of 2D materials, both theoretical and experimental, on both institutions, INL and University of Minho.